So this video is a continuation of what we just compared ideal velocity, which is 1.84, and the experimental velocity of 1.594 meters per second. So it means that we want this velocity. This is the velocity that we think we will get when we let go of a cart from a certain height and ending up to this position, and because of different factors, your velocity doesn't match with the ideal velocity. Okay? So this is the real world, while this is my desired world, utopia, as we call it. So this is what it's supposed to be, but this is actually what's going on. And that difference can be attributed to losses in terms of converting energy, but it doesn't mean that energy was already destroyed, but instead it is used to overcome other factors such as friction or parasitic load, or maybe air resistance if there's any, and there's other factors like but most of the time we will consider friction as the culprit. Okay? Because of the wheels, maybe they're not properly lubricated, and it's starting to eat up metal to metal, and it doesn't have bearing, but instead it's just an axle or a shaft that is placed in a hole with the wheels attached to it. And also maybe we can say that because of the ramp is a little bit slippery, so it slips. So this time friction wasn't there, or friction, the desired friction was not enough in order to keep traction. So that's when we put in the factor of efficiency. So efficiency, so let's figure out the efficiency of the ramp system. So efficiency is simply, which is expressed in terms of percentage, is simply our energy output. So I will just put E in or E out, which stands for energy output, and then E in is the input. So usually the input energy is greater than the output energy, and then let's multiply it by 100%. That's why it's called percentage. Okay. Now, first thing is to figure out the output energy. The output energy, if you notice, I still have my calculation from my previous video. So this side over here is considered our output. So this is E out. While the left side of the equation is your E in, the input energy. So using these equations right here, let's calculate our input and output energy. Okay. Input and output energy. So for input, since we all know it's everything is potential, so for our input energy, so let's put it here, E in. Still wanted to write it down, mgh plus 1/2 mv sub naught squared. So this means that at this point, the initial velocity is 0. Don't forget that. So let's plug in the values, which gives us m times 10 times 0.9, 0.19, 0.19, not 0.9, plus 1/2 m0 squared. And right away we know that this is 0. So energy in is simply our mass multiplied by 10 times 0.9, which is m1.9. So this is our energy in. Input energy of 0.19. Now using a different color, so how about our energy out? Same equation, so mgh, but this time instead of using the uppercase h, let's use the lowercase h of 0.02 plus 1/2 mv squared. Okay. So mv squared. But this time, instead of using the velocity, okay, instead of using the velocity of 1.84, we will use 1.594. Okay, so 1.4594. So let's try to figure out this solution right here. So this will give us m times 10 times 0.02 plus 1/2 our mass times the square of 1.594. Okay. So I don't want to bore you anymore by going step by step. Let's just use our handy dandy calculator to multiply, and this will give us m.2 plus 1.594. Let's square this, and then let's divide it by 2, as it says half, and this will give us m times 1.27. 0.27. So when you add those two numbers together, now we have a mass multiplied by 1 point, so that's 2 plus 2, so 47 in terms of energy. So right away we know that the amount of energy is not how would I call this, the same. So we can say that the efficiency is definitely not 100%. It's not 100%. It's not 100% based on this experiment. So now let's plug in those values. We can say that the percentage or the efficiency is simply, but we have the m. Okay, so we have the m. So how can we solve if it's a variable? So let's take a look. So let's put our energy in, energy out, which is 1m multiplied by 1.47 divided by m multiplied by 1.9, and then let's multiply by 100%. M cancels out, so our energy in terms of percentage is simply right here using a calculator, 1.47 divided by 1.9, and let's multiply it by 100. So it means that the ramp, based on this experiment, would have an efficiency of 77%, 77.37%. So with this video, you can use this to calculate the efficiency given an experiment that you have a ramp that is going down, or a cart that's going down a ramp. Okay, going down a ramp. So this is the efficiency. But what if, my question is, if we use the same velocity here? Okay, so what will be the efficiency if we use this velocity? For sure we will get 100%. It's because this is what it's meant to be. We want this velocity, and velocity will dictate the amount of potential energy right here. So for example, let's replace 1.594. What if we replace this by 1.84? So what I'm going to do, I'm just use the small space over here. Let's use this small space to calculate the energy. What if it's 1.84 instead of 1.594? What if velocity is 1.84 meters per second? Let me use a different color so you can see it. Again, this one will be the same. Okay, so this section over here will be the same. So I'm just going to write it down, 0.02 or 0.2 plus 1/2 m and then 1.84 squared. So let's square this number. 1.84, square it, and let's divide it by 2. So this will give us 1.6 So 1.69. 1.69 plus 0.2. So this will give us m.2 plus 1.7. Okay, 1.69 or 1.7. So m times 1.7. So therefore we will have an output energy that is equivalent to, so 0.2 plus 0.7 will give us 1.9. If you notice, 1.9, 1.9. So if you plug in that value, it will have 100% efficiency. Okay, 100% efficiency compared to 277.37% efficiency. Hope this video will help you a lot, and see you in the next video.